Concealed beneath Saturn's moon Titan and its hazy orange atmosphere lies one of the most profound mysteries in our solar system. A world exists down there that bears striking resemblance to our own, something eerily familiar, yet simultaneously alien and incomprehensible. Naturally, the only way to truly understand what's happening out there is to land on this moon and explore it firsthand. This is precisely what NASA intends to accomplish with their forthcoming Dragonfly mission, a nuclear-powered helicopter designed to soar through Titan's skies while searching for extraterrestrial life. What we've already learned about Titan is nothing short of remarkable. It stands as the sole moon in our solar system possessing an atmosphere, and this atmosphere is remarkably dense, 4 times thicker than Earth's. Much like our home planet, the majority of Titan's atmosphere consists of nitrogen. However, unlike Earth with its life-sustaining oxygen mixture, Titan's atmosphere is saturated with methane, more widely recognized as natural gas. That substantial atmosphere actually produces an inverted greenhouse effect, obstructing what minimal solar warmth manages to reach these distant reaches. As we descend deeper toward the surface, that methane grows progressively colder until it transforms into liquid and descends as precipitation onto a surface composed of ice as rigid as granite stone. The outcome is a network of flowing rivers, lakes, and seas of methane streaming across Titan's landscape, making it the only known celestial body besides Earth that maintains an active hydrological cycle and stable surface liquids. Also mirroring Earth, Titan exhibits a diversity of terrains. Beyond the rocky coastlines, expansive deserts stretch across the moon's equatorial regions, featuring elongated dunes sculpted by persistent winds. However, this isn't sand. It's a granular organic substance that has likewise descended from the atmosphere and accumulated atop the frozen ice rock. We lack definitive answers regarding what this material actually is, where it originates, or whether it might potentially harbor signs of life under appropriate conditions. Speaking of life, Titan possesses abundant water. A liquid water ocean exists beneath the surface, heavily saturated with salt that prevents it from solidifying. Occasionally, water erupts onto the surface like slushy volcanic flow from a cryovolcano. Additionally, very few impact craters remain visible on Titan, indicating that the moon's surface undergoes constant transformation and regeneration, much like Earth. When we consider all these elements together, water, nitrogen, carbon, and organic molecules, we find all the essential ingredients for life as we understand it. Yet the environmental conditions on Titan would suggest that life couldn't possibly survive here, at least not in any form we recognize. Still, we acknowledge that there remains much about the universe and the fundamental nature of life that we don't comprehend. Therefore, we anticipate that our expedition to Titan will yield fresh insights. This won't mark our first visit to Saturn's remote moon. Everything we believe we understand about Titan stems from the Cassini probe, launched toward Saturn in 1997, which studied the planetary system from orbit for numerous years. But Cassini also carried along a particularly special additional payload, a lander designated Huygens, named in honor of the Dutch astronomer who initially discovered Titan in the night sky. Due to the thick haze enveloping the entire moon, studying Titan from afar proves impossible. We must approach it intimately. Cassini released Huygens above Titan, and the lander commenced its descent through the atmosphere, which isn't merely thick but extraordinarily tall. We previously believed Titan was considerably larger than it truly is, hence the name, because it's inflated by such an extensive atmosphere. After deploying its parachute, Huygens spent 2.5 hours drifting downward to Titan's surface. It managed to capture these photographs after finally penetrating the dense haze and approaching for landing. Bear in mind, these are images taken with a digital camera from the mid-1990s, transmitted live to Earth across more than 1 billion kilometers using the Cassini probe as a relay. Consequently, the image quality isn't exceptional, but we can discern cliffs of icy rock carved through by flowing streams and rivers of liquid methane. Huygens touched down on the soft, sandy floor of a dried riverbed. The final site it captured before shutting down showed these rocks, smooth and rounded by erosion, just like river stones on Earth. Except this isn't stone. It's solid ice. Naturally, we must return to Titan's surface to discover more. This is why NASA has engineered their Dragonfly rover. It differs from any rover we've encountered before. This one shares more similarities with a contemporary quadcopter drone. The only other extraterrestrial location where we've successfully flown anything is Mars, which possesses 37% of Earth's gravity and less than 1% of its atmospheric density. The fact that NASA managed to fly their Ingenuity drone at all came as a welcome surprise. Ingenuity completed 72 flight missions on Mars across 3 years of operation. During that period, NASA acquired extensive knowledge about piloting drones from millions of miles away, and they're currently applying all that expertise to the Dragonfly project. Only this time, they're scaling up considerably. A larger drone demands a more substantial power source. While Ingenuity drew its energy from a small solar panel, Dragonfly will operate too far from the sun and remain sheltered beneath too much cloud coverage. To explore Titan, NASA must employ nuclear power, the same energy source they've utilized for Mars rovers since Curiosity back in 2011. This isn't a nuclear reactor like what you might envision in a power plant. These deep space explorers utilize a radioisotope thermoelectric generator, which is essentially a mass of radioactive plutonium that produces heat as it decays, and the generator converts that thermal energy into electricity. Dragonfly measures just over 3 meters in length and weighs approximately 450 kilograms on Earth, though due to Titan's relatively modest size, the gravity there will be merely 14% as intense. That's remarkably close to the gravitational force on Earth's moon. When you combine that reduced gravity with the dense atmosphere, flying on Titan becomes an extremely efficient and practical method of transportation. Dragonfly is also configured as an octocopter, featuring 8 propeller blades, each slightly over 1 meter in diameter. This design provides a level of redundancy. The machine doesn't actually require 2 propellers at each corner to fly, but this means that if one fails, the mission won't be terminated. That's crucial because this represents a tremendously lengthy and expensive undertaking for NASA. Dragonfly has been under development since 2017, and it actually evolved from an earlier proposal that would have deployed a balloon to drift above Titan. As with most sophisticated space exploration missions, schedules can prove challenging to establish firmly, but Dragonfly does have a launch window. Designated for July 2028, NASA has already secured the SpaceX Falcon Heavy for the assignment. Reaching all the way to Titan within a reasonable time frame won't be simple, even with a launch vehicle as powerful as the Falcon Heavy. Their strategy involves launching the probe toward Venus first. Then Dragonfly will execute a slingshot maneuver around Venus, harnessing the planet's gravity to accelerate. Then it actually returns to Earth and performs another gravitational assist to gain even greater velocity before Dragonfly finally sets its trajectory toward Titan. This entire process should require 6 years. Dragonfly will arrive at Saturn, positioned 1.2 billion kilometers from Earth, in 2034. The final approach to Titan will constitute a direct ballistic entry, meaning the vehicle won't establish orbit and then gradually descend. We are striking Titan like a projectile. After separating from its cruise stage engine, the entry capsule essentially functions as a heat shield with a dome-shaped protective cover on top. The heat shield employed by Dragonfly will closely resemble what NASA utilized when the Perseverance rover landed on Mars in 2021. The heating phase of entry should persist for approximately 6 minutes. That's the first critical moment. Then, once again mirroring a Mars rover, once the probe has penetrated Titan's atmosphere, a supersonic drogue parachute will deploy to begin reducing velocity. This phase should proceed relatively smoothly. Dragonfly will spend 80 minutes descending on its initial parachute. Then, once we're moving at a sufficiently slow pace, the heat shield will be jettisoned and the main parachute deploys. The final descent phase continues for another 20 minutes. At 1.3 kilometers above Titan's surface, circumstances become tense again because Dragonfly won't be landing under parachute. Maintaining the same profile as recent Mars landers, Dragonfly will detach from the parachute and activate its own propulsion system. On Mars, this has been rocket engines, but on Titan, it will be propellers. So it's a trial by fire for this drone. Either it functions immediately or it plummets like a stone. Assuming it does operate correctly, Dragonfly will hover downward for a gentle landing on Titan's surface. The selected landing zone resides in a region named Shangri-La, a reference to a fictional location in the Tibetan mountains from a 1933 novel called Lost Horizon by author James Hilton. It's an intriguing choice. given that this region of Titan more closely resembles the planet Arrakis from the Dune series by Frank Herbert. Dragonfly will make contact with a flat plain bordered on both sides by massive wind-carved dunes. These dunes average 1 to 2 kilometers in width, 100 meters in height, and they extend for hundreds of kilometers. The sand on Titan isn't composed of silicates as we know on Earth. It's actually solidified hydrocarbons that precipitate from the sky. So it's somewhat like an extremely hard, grainy snow, if that snow were made from gasoline. Since carbon serves as the fundamental building block of life as we understand it, these carbon-based particles are classified as organic compounds. This doesn't mean they're alive, but it indicates they might become alive if provided the proper set of circumstances. What precisely those circumstances are remains largely uncertain. But if these organic compounds are mingling with the subsurface water on Titan, then there could very well be something living down there. In any case, that's the primary objective that Dragonfly will be investigating. The drone might travel through air, but its most vital scientific work will be performed on the ground. Dragonfly's principal instrument is a drill that will bore into the surface to fragment the frozen ground and create loose dust that can be drawn into the drone like a vacuum cleaner and conveyed through a series of tubes into a sample collection apparatus. Each time, Dragonfly collects a sample. It is stored in an individual small container. That container is then transported internally to a device that will essentially bombard the sample with a laser to break the material down into its constituent molecules so they can be identified. Then, if the assembly of molecules in the sample proves particularly intriguing, the container is conveyed to an oven inside Dragonfly that vaporizes the molecules into a gas that can be even further decomposed, sorted, and analyzed for its specific chemistry. What scientists are seeking specifically are biosignatures, evidence of very primitive bacterial life. The concept here is that the conditions we observe on Titan presently closely mirror what we believe the conditions of early Earth resembled, where hydrocarbon material descended from the sky and combined with water to form the primordial soup from which all life emerged. That's the theory at minimum. To conduct this research, Dragonfly will spend 3 Earth years, or 764 Titan days traversing the surface, soaring over dunes and landing in the valleys between them. Dragonfly is projected to travel over 180 kilometers and investigate 24 distinct sites. Dragonfly will lift off once per Titan day, which occurs every 16 Earth days, traveling in the daylight and then settling down to collect samples and analyze them until the next dawn. This means the majority of its operational time will be spent on the surface, taking measurements and transmitting data back to Earth. While the mission commences among the desert sand dunes, the probe's concluding days will be devoted to investigating a large crater designated Selk, where it's theorized that organic compounds were able to mix with liquid water, following an asteroid impact that penetrated the ice barrier. The one location of interest that Dragonfly will not be visiting is the methane seas. In fact, it's improbable that the drone will encounter any surface liquid whatsoever, and that is disappointing. But there's a valid reason. It's believed that at one point in time, most of Titan was blanketed by rivers and lakes, but over the course of billions of years, the surface liquid has receded almost entirely to the moon's north pole. That's where we would need to venture to discover it. Unfortunately, landing at the polar regions of a planet or moon ranks among the most challenging operations imaginable. We're still genuinely struggling just to land at the south pole of our own moon. So attempting the same operation 1 billion kilometers away on Titan would present excessive risk. Traveling that distance and then crashing would constitute a catastrophe for NASA. So landing at the equator represents the straightforward solution. And with a mission of this magnitude, simplicity is paramount to success. And it's not as though Titan is disappearing. We don't need to accomplish all the science simultaneously. A decade from now, who can say what scientists and engineers might be capable of achieving? We'll have advanced technology, new rockets, enhanced capabilities to dispatch even more remarkable machines out into the deep solar system and discover phenomena we never even imagined possible. But Dragonfly truly represents an extraordinary first step toward extending our reach far beyond Earth, and that is something genuinely exciting to anticipate.